Hello all and welcome back. In today's video I want to get the LCD screen up and running and then do some programming. Once this is done, then I think it's about time to put what we have onto PCBs and get rid of all these wires. So the next video I'll be showing you that and getting the boards ordered. This display that I'm going to add to the Pony80 is a typical 2-line by 16 character LCD with the microcontroller built in. This makes it very easy to interface to our CPU since there are only 3 control lines and 8 data lines. Now if we look at the data sheet, you can see that 5 pins provide power. Pins 1 and 2 provide power to the microcontroller and the display itself. Pins 15 and 16 provide power to the backlight. And pin 3 controls the contrast. On pin 4 we have RS, which sets whether we are sending a command to control the display or data to show on the display. Pin 5 is the read-write pin, which allows us to select if we are writing to or reading from the display. And pin 6 is the enable pin. So we're going to set this up so we can write to it using an I/O call, just like we did on the ROM page I/O port on the memory card. This time though, we're going to use a 74HCT138 3 lines 8 line decoder for the selection. This chip takes in 3 lines of data along with 3 enable lines and puts a low on one of the 8 output pins depending on the 3 inputs. Let's take a look at the truth table for this. You can see here that we have one active high enable pin, G1, and we have 2 active low enable pins, G2A and G2B. This is convenient since we have to check for M1 high and IORQ low to enable an interrupt. We can use address line 4 as the other low enable source. And then we can use A5 through A7 to select which port we want. So for example, if we send an output to port 0, M1 would be high, IORQ would be low, A4 would be low, and that would enable the chip. And then A5 through A7 would also be low, which would cause the Y0 output pin to go low. Now that sounds like we are wasting a lot of I/O addresses since we're not using A0 through A3, but I think for our case it'll work fine. We will have the ability to add 8 I/O ports like this, and then if we invert A4 on future decoders, we open up a whole new set of 8 ports. And on each board we have the ability to decode A0 to A3, which gives us the ability to use up to 16 ports per I/O card. However, I don't envision that we'll need too many I/O ports on this machine, so this should work out fine. So the HCT138 will provide the enable signal for the LCD. However, the LCD expects a high signal and we get a low out of the chip, so we'll need to invert it. The command pin on the LCD will be connected to A0. This allows us to send the command to port address 00 and the data to port address 01. Again, multiple ports within one card. Now on the read-write pin, you can see that if this pin is low, we will be writing, which is great because the CPU write line is going low to indicate a write request. However, this is where the details make a big difference. If we look at the timing diagram for the LCD write function, you can see here that it looks like it is expecting the write signal to go low before the enable pin goes high. And then again at the end, it wants the write signal to stay low after the enable signal has gone low. So let's look at the detailed timing here and see how long it needs to be on each side. If we look at TAS, or address setup time, you can see it needs 0 nanoseconds. This is good because the Z80 will set the enable pin and the write pin at the same time. However, if we look at TAH, or the address hold time, you can see it needs write to stay low for 10 nanoseconds after the enable signal goes low. This is going to be a problem that we will need to work around. Now, since we have to delay that low, I thought of a couple of ways of doing it. One is going to be using something like a 74HCT04 inverter. If we look at the specs, you'll notice a propagation delay of several nanoseconds, so we could invert the write signal a couple of times and rely on that delay to work. And it does, I've tested it. However, those propagation delays can vary chip to chip, and to be safe we would probably need to invert the signal 4 times using 4 inverter ports. But there's another way to make this work. If we invert the read signal from the CPU and use that to indicate a write, we would have a lot more consistency. The datasheet for the LCD states that reads also need that 10 nanoseconds after the enable goes low. However, that doesn't seem to be the case in real life. So now that we have that worked out, we can get to the build. Let's break out a new breadboard and mount the LCD. Okay, let's get a power hooked up here and ground. And then we'll get the LCD added to the board. There we go. I'll go ahead and I'll hook up ground to pins 1 and 16 and power to pin 2 and 15. Not necessarily in that order. Now the contrast works using a trim pot with the ground and 5 volts on the outside legs and the signal for the board coming from the middle pin. So I'll get that hooked up and I'll add power and ground. And then hook the wiper up to pin 3 of the LCD. Now I want to set up the 74HCT138 to do the port address decoding. So let me put that here and hook up power and ground. And now I'm going to connect the M1 IORQ A4 through A7 from the CPU to the HCT138. You're not going to be able to see it over here on the board, but I'll put a finished picture of it, or I'll put a picture of it when I'm finished so you can see all of the where all the wires are. Right now it's a mess, which is why we've got to get it to the we've got to get it onto PCBs. And I'm going to connect IORQ to pin 5. And then finally M1 to pin 6 there. And then I'll just stick this extra wire here so it isn't floating. Now I'm going to connect A0 to pin 4 of the LCD. This will give us our command/data signal. There we go. And I'm going to invert the read signal from the CPU on the inverter over here on the original breadboard and connect it to pin 5 on the LCD. There we go. And now I'm going to invert the Y0 output from the HCT138 and hook it up to pin 6 on the LCD for enable. There. And then we just need to hook up the 8 data lines. I'm going to pull them off of the ROM chip here at the bottom of the screen. And finally, connect power to the main board. And now it's assembled, but it's not going to do much until we change the programming. So let's go do that. Let's take a look at the LCD datasheet to see what we need to do to print characters. This flowchart shows what we need to do on startup. We have to wait for 40 milliseconds after voltage reaches 4.5. This will be easy since our reset circuit holds everything in reset mode for a second upon boot up. Then we need to send a function set command. Let's take a look at that. The function set command has zeros in bit 7 and 6, a 1 in bit 5 to indicate the command, and then bit 4 lets us select between 8-bit interface and 4-bit interface. We want to use 8-bit, so it looks like we would set that pin high. Bit 3 is the number of lines to display. We want 2, so we'll set that high as well. Bit 2 allows us to select the font type. We'll set that high as well. And the last 2 bits don't matter, as indicated by the dashes. So we need to send a 00111100 to the command port of the LCD. Let's do that. This is the old program that we had to test the ROM and RAM. I'm going to get rid of that. And let's start with a label, LCD init. Just keeps the code looking cleaner. And we'll load our value into A, 00111100. And then we will output that command to the command port. But rather than type in the $00 each time, let's make the code a bit easier to understand by giving that value a name. We'll call it LCD CMD and set the value to 0. And while we're here, let's go ahead and set up LCD data and set that value to 1. These are the 2 ports that we configured using A0 on the circuit we built. Now we can output the contents of A to the LCD command port. The next thing we need to do is call the display on-off command. Let's take a look at that. The display on-off command needs a 1 in bit 3, and then bit 2 is going to indicate if we want the display on or off, so we'll set that to a 1. Bit 1 indicates if we should show a cursor or not, so we'll also set that to a 1. And bit 0 indicates if the cursor should blink. Let's set that to 0. So our display on-off command is going to be 00001110. Let's go to take care of that. Now the next step is to clear the display. The clear display command is pretty easy. We just have to send a 1 in bit 0. And finally, we have to set the entry mode. This command needs a 1 in bit 2, and then bit 1 indicates if we want to increment or decrement the pointer to the memory address after we send a character. We'll set this to 1. And bit 0 indicates if we want to shift the display as we send characters. We'll set this to a 0 since we don't want to do that at this time. So our instruction becomes 00000110. So now that we have this set up, we should be able to initialize the LCD. But I think I'm going to optimize this code a bit. It may not look like much, but as written, this code takes 72 clock cycles to run. So rather than write out 4 discrete output sequences, I want to wrap this into a loop. So first, let's go down here and add our commands as hard-coded values with the label LCD init message. Again, with this label, the compiler just replaces it with the memory address it occupies. So let's get the full set of commands down here and end it with a 0 to indicate end of message. And now we can go back up here and load HL with the memory address at LCD init message. And once we have that done, we can start the loop. Let's call it LCD init loop. Now we'll load the value in the memory location stored in HL into the accumulator. And then we can AND it, which will set the 0 flag if the value in memory is 0. And if it is 0, we need to jump somewhere. Let's call it main. Now if the value isn't 0, let's output that to the LCD command port. Once that's done, we'll need to increment HL to go to the next memory address and jump back to the beginning of the loop. So now that we have this, we can get rid of the individual statements. Now this code, as it's written, takes only 57 clock cycles compared to the 72 of the discrete statements. Well, now that we have the initialization done, let's print some. Up here we have the jump to main, so let's create that and send something to the LCD data port. We'll start with something simple, like an A, which is ASCII code 65. We'll send it to the data port. And then we'll halt so we can see that it stopped. We've got that LED on the breadboard that will go low when the halt command is encountered, so we'll be able to see that. And we'll save and compile. Uh-oh, looks like we got an error. Let's take a look at line 26 here. You can't have these values on separate lines like this in assembler. So let's fix that. So let's save and compile again. And there we go, we've got it. So now we just need to burn this into our ROM and put it on our breadboard. Let's see what happens. All right, so let's get the ROM plugged into the breadboard and power it up. And there we've got our A. That's exactly what we're looking for. If we look back at the data sheet for the LCD, you'll notice the busy flag. And under that, it states that if the busy flag is a 1, the next instruction will not be accepted. So we need to have a way to read bit 7 of the command port and wait for as long as that value is 1. So let's go back to our code and set up a routine to wait for the busy flag to be cleared. We'll call it wait LCD. The first thing we want to do is push the accumulator onto the stack so we don't overwrite anything the calling program has stored there. That's just good programming practice. And then we can set up our loop. We will load A with the LCD command value using the in command, and then we'll rotate the bits one place left, which will move bit 7 to the carry flag. So if the carry flag is set, we want to continue waiting, and we'll jump back to the loop label. If the carry flag is clear, then we'll pop AF from the stack and then return back to the calling program. Now, since we're going to be using the stack, we will need to set the stack pointer register. For now, we'll just set it to the top of memory. Remember that the stack pointer writes from a higher address to a lower address going downwards in memory. Now down here in the LCD init routine, let's call the wait LCD subroutine. So let's go ahead and add some other helpful subroutine. Let's call this one display message. This will perform the same steps as the init LCD routine, but we can set where the message is coming from. So first thing is we'll load A with the value and memory address HL. To determine if we're at the end of the message, which is indicated by a 0 byte, let's AND the accumulator. Now if A is 0, we can jump to the message done code. Otherwise, output the A value to the LCD data port, and then increment HL, and then jump to the display message loop to process the next character. And when the message is done, we can pop AF back to the stack and then return. Now let's set up our message. Hello world seems appropriate. And then we can load HL with the address of the message to display and get rid of all this code and just call display message. Oh yeah, one more thing. Let's terminate the message with a 0. Okay, now we're going to save, compile, and burn to the ROM. And let's test it. So I'll put the ROM back in the breadboard here. There we go. And then I'll plug in the power. And voila. Hello world. Well, thanks for joining me. Next episode, we'll add some more routines for printing, and then we'll start designing PCBs to get rid of all these wires. So please like, share, subscribe, ring the bell, all that other stuff. And visit my website, which has the full schematics along with other helpful links. And until next time, enjoy.